Greetings and welcome to lecture 3. Today we will talk a little bit about convex sets, but before we start that, let us review a little bit what we did in the last couple of lectures. The setup is as follows. We are talking about a metric space X, which is compact and comes with its Borel sigma algebra Bx. On the Borel sigma algebra, of course, we have plenty of probability measures, and we call the set of all of them Mx. The space of continuous functions with the supremum norm is denoted by Cx. The Ries representation theorem tells us that Mx naturally embed in Cx star, the dual of Cx, and we use the weak star topology on that space. With this setup, we know that Mx has some very nice properties. It is compact, which we proved in the previous lecture. It is convex. By convex, we mean that it's closed under convex combinations. So if we take two probability measures in Mx, call them mu1 and mu0, and we take a number between 0 and 1p, we get a new measure, mu sub p, which is the convex combination of mu0 and mu1. That convex combination is also in Mx, and finally Mx is not empty. The last 2 points are very easy. For non-empty, you can take, for instance, the measure that we call delta x before. That's the measure that assigns 1 to any set that contains a point x and 0 to any set that does not contain a point x. Here in delta x, it's a little bit too difficult to see with these fonts, but little x here is supposed to be a point in capital X. The convex, being closed under convex, is also quite easy, and we will leave that as an exercise. So, in order to understand this space Mx, we have to have some understanding of sets that are compact, convex, and not empty. And what we will do today, I think it will be a relatively easy lecture, is discuss some facts about convex sets in finite dimension, in Rn. Of course, Mx does not live in a finite dimensional space, so the generalization will not be completely straightforward. So let's start with the definition. A set M that will be a finite dimensional analog of Mx in Rn is called, suppose we are given a set M in Rn. A convex combination of points in M is a combination of the form sigma pi xi, where the coefficient pi, you can think of them as probabilities, are all non-negative and sum up to 1. Given a convex set such as M, a set M is called convex if it's closed under a convex combination. A point in this convex set M is called extremal if it's not a non-trivial convex combination. By non-trivial convex combination, we mean a convex combination such as this written over here, where at least 2 of the pi's are not 0. So a point is extremal if whenever we show it as a convex combination, all the pi's are 0 but 1, which equals 1. And of course, if one of the pi's equals 1, then the corresponding point xi necessarily must be the point x itself. The extremal point will end up playing a very important role in our game, so we give that set a name, or a notation rather, which is curly E. So let's look at a few examples in finite dimensions. This entire lecture will only be in Rn. A closed triangle, and by closed triangle I mean including the area that it bounds, a two-dimensional gadget in R2 is convex, and the extremal points are the vertices. Of course, a point in the interior is not going to be extremal, because you can go a little bit to the right and a little bit to the left, or up and down, whichever direction you choose. Take a couple of points and do their convex combination. A point on an edge, in the interior of an edge, is also not convex, because you can still go a little bit to one side, a little bit to the other side, and see a non-trivial convex combination. And I'll leave it as an exercise for you to see that the vertices are in fact extremal. A closed disk is also convex, and the extremal point of a closed disk consists exactly of the boundary circle. This shows an example, of course, that the extremal points are not finite. The set of extremal points is not finite. It's not hard, I think, to see that a point on the boundary must be extremal. Take a line that's tangent to the point on the boundary. Except for that one point on the boundary, all the points of the disk are to one side of the line. So let's suppose, for simplicity of the discussion, that the line is vertical and the disk is to the right of the line. Then all the points of the disk are strictly to the right of the line, except the point that is the point where the line is tangent. Any linear combination that has any of the points that are strictly to the right of the line with a positive coefficient will result in a point which is strictly to the right of the line. It's simply the same as when you do an average, because that's what it is. A convex combination is a weighted average. An average of numbers in R, if none of them is negative and at least one of them is strictly positive, the average will be positive. An open disk is also convex, but it has no extremal points at all. In fact, the entire space Rn is convex, but also has no extremal points at all. Another example of a convex set with no extremal point is an upper half plane. And again, if you want to simplify it a little bit, you may want to start with an open upper half plane. But the closed upper half plane is more interesting, because then you might expect, similar to the closed disk, that the boundary will consist of extremal point. But that is not the case. The boundary looks more like the boundary of a triangle, and every point on the boundary of the closed disk looks like the point in the interior of an edge of a triangle. So if you take a point where y equals 0 and x is some number, you can show it as the convex combination of x plus 1, 0 and x minus 1, 0, both with coefficient 1/2. The last example we can take as m, again something a little bit similar to the closed upper half plane. We can take all the points x, y, where x is greater than or equal to e to the x. This is convex, and the extremal set of points now is not empty. In fact, it consists of the entire boundary, all the points x, y, where y equals exactly e to the x. So perhaps this gives us a feeling that things are not so good, because in some examples we have extremal points and some are not extremal points, and we declared that extremal points are very important to us. But all the examples that were strange were non-compact. And in the compact case, we have the following proposition. Suppose M in Rn is compact and convex. Then every point of M is the convex combination of its extremal points. In particular, of course, this means that there are extremal points, except for the case where M is the empty set. The proposition still holds vacuously, but we won't concentrate on that too much. So a good point right now is to go back and look at all the examples from before. You'll see there plenty of counter examples when compactness is lost, and you can ask yourselves as an interesting exercise, what happens for the set xy, which was defined by y is greater than or equal to e to the x, the last example on the previous slide. In that case, there are extremal points, we already discussed it, but does the proposition hold? Is it true that every point in this specific set is a convex combination of extremal points? So let's discuss a little bit the proof of the proposition that we just mentioned. The proof is an induction on n, and the induction starts when n equals 0. n equals 0, there is actually nothing to show, because at n equals 0, R0 is a single point. There's only one convex non-empty set, and it consists of a single point, which is the extremal point. Let's consider the case n equals 1, even though technically we don't need it for the induction, but just to get an idea of what things look like. Well, if we have a non-empty, compact, convex set M in R1, in particular because it's compact and non-empty, it attains its supremum and its infimum, We can denote those by B and A. Because the set M is a convex set in R, it has to be an interval. A set in R is convex if and only if it's of the form of an interval. Of course, this interval may be unbounded, it may be open, half open, any kind of interval goes. But this interval is compact, which means it's bounded as closed. So we see that what M is, it's simply, as is written here, a closed interval from the infimum A to the supremum B. Well, now we know exactly what the extremal points are. They are A and B. And every point of M, of course, is a linear combination of these two extremal points. Now let's think a little bit about the inductive step. We're given a set M in Rn, which we are told is convex, compact, and let's also assume non-empty, otherwise the proposition is vacuous. For any point in R, we can get a hyperplane. A hyperplane is simply an affine subspace of dimension n-1, where affine subspace is a translate of a linear subspace of the same dimension. We can get a hyperplane by setting the equation, for instance, xn equals to the constant c. Because M is compact, it is bounded in Rn, and so hence for very, very large C, we have that this intersection of the hyperplane with M is empty. Let's look at A, which is the supremum of all the points where the intersection is non-empty. Then the claim is that when we look at M intersect P sub A, we get a convex, compact, and non-empty set. Now, convex and compactness, the footnote here discusses a little bit the proof of this claim. Convex and compactness is very easy because it is the intersect of two convex sets, therefore it is convex, and the intersection of two compact sets, and therefore it is compact. Non-empty is a little bit more fun. If you want to show that this set is non-empty, of course you must use the fact that M itself is non-empty, but this is not enough. You can think about what happens if M, for instance, is an open unit ball around the zero. Then A is the number 1, and PA is a hyperplane defined by xn equals 1, and that is in fact disjoint from M. So to prove that this is not empty, you need to use that M is not empty, but you also need to use compactness of M. Now PA itself is an n-1 dimensional Euclidean space, not as a vector space, but geometrically, and induction applies, and it shows that M intersect PA admits extremal points. Of course, the extremal points are extremal points of M intersect PA, and I'll leave it to you as an exercise to show that an extremal point of M intersect PA is also an extremal point of M. The induction gives us more though. The induction also tells us that if we look at M intersect PA, every point of it is a convex combination of the extremal point in M intersect PA, and the next exercise asks you to prove, using that fact, that every point of M is a convex combination of its extremal points. I think this is kind of a fun exercise. It is well, it's an exercise, so I shouldn't say too much, but I do recommend before you do this exercise to try to see what happens if you take, for instance, a closed triangle in the plane. Of course, every point of the triangle is a convex combination of the extremal points, which are the vertices. That's not really hard to see. But it does show a few things. For instance, if you want to show every point in the triangle as a convex combination of 2 points, well, these points will not in general be extremal. Combinations of pairs of points gives only the boundary of the triangle. It gives the edges. If you take 2 vertices, the convex combinations give exactly the edge. And it also shows that if you look at a line through a point, well, if you choose it very carefully, which you really shouldn't do in this proof, then it might go through one vertex and then you get one extremal point, but you will not get a line that goes through 2 extremal points if you start with a point in the interior of the triangle. So there's a couple of things to think about as you review today's lecture. One is we defined convex combination as a combination of finitely many points. Some people would define it as combination of 2 points. If you're closed under combination of 2 points, then by induction you are closed under combination of finitely many points. Combinations of 2 points give segments. And that means the following. A set is closed under convex combination of 2 points if the following condition holds. If I give you 2 points in the set and you look at the segment connecting these 2 points, the straight line segment, then this straight line segment is completely contained in the set. And of course, that's the way convexity is usually defined. It just seemed more convenient for the discussion that we had today to define it in a slightly different way. And maybe it will also be more convenient for the discussion next time. So that's really all that I wanted to say about convex set in Rn. I suspect maybe you've seen some of those before, maybe it won't be so difficult, but it's worth thinking about them a little bit, because in the next lecture we will talk about convex sets in infinite dimensional space in Cx star, which is where Mx lives. And of course, things get a little bit trickier when you talk about infinite dimensions, which is why I think it's worth reviewing what happens in finite dimensions. That's it for today, and I'll upload the next lecture as soon as I possibly can. Maybe by the time you listen to this, the next lecture is already available. I'll talk to you then. Bye.